In this equilibrium revision, we'll try to be as fast as we can to know what is the difference between the equilibrium and the steady state. The equilibrium is a reaction in which there is a forward reaction and backward action, or two processes happening at the same time in opposite direction, and the system is closed. But if the system is open, even if there is two processes happening at the same rate and in opposite direction, and the system is open, then it will not be called equilibrium, it will be called a steady state. Like if you have a bottle of soda and then the bottle is opened and the gas is going out and some carbon dioxide is depositing or condensing, and the bottle is open, then it is steady state. If it is closed, then the condensation is opposite to evaporation, and there is two processes, but this is closed, so it will be called equilibrium. There are two processes known. The microscopic processes are the processes that I don't see or I cannot measure. And this is like the molecules binding together or the molecules breaking into smaller atoms. So this means that this process is microscopic, and in equilibrium, these microscopic processes are not stopping, they are continuing. And the macroscopic processes are the processes that I can see, that I can measure, like the color, like the pressure, like the volume, like the concentration. These are things that I can see and I can measure. In the equilibrium, this macroscopic process stop. I don't see any changes happening. In the equilibrium, all the macroscopic processes continue to happen, although there is no macroscopic changes. The dynamic equilibrium is when I define equilibrium as the process in which the rate of the forward reaction is equal to the rate of the backward reaction without the stopping of the microscopic process. So this is two processes happening at the same time, and no stop of the microscopic process is known as the dynamic equilibrium. This is versus the static equilibrium, in which there is no changes at the beginning. The low Chatelier principle is the principle which tells me what is the effect of changing any factor on the equilibrium. It can predict the change of equilibrium concentration for any reaction. If there is a change in the pressure, if there is an increase in the pressure, the system will try to decrease the pressure to oppose what I have increased. So it will try to move to the direction of less moles. And if I have increased the pressure, if I have decreased the pressure, the system will try to oppose that by increasing the pressure by moving in the direction where there is more moles. If there is a change in temperature, there is an increase in temperature, an increased temperature, system will try to decrease the temperature by moving towards the endothermic direction. And if I decrease the temperature, the system will try to increase the temperature by moving towards the direction of the exothermic direction. If I have increased the concentration of any reactant, the system will try to decrease this concentration by moving in the opposite direction, which does not form this reactant or product. If I decreased it, the system will try to increase its concentration. There is no effect of changing the inert or addition of inert gases on the equilibrium, as they don't interact with anything, and there is also no effect of adding catalysts on the equilibrium. It only causes the equilibrium to happen faster, but the direction does not change. It does not move forward or backward. So equilibrium will happen faster, but there is no change in the direction. If there are two directions which have the same number of moles and you have changed the pressure, then there is no change. It will not move either forward or backward. If there is a solid or a gas, a solid or a liquid in the equation, then I will not consider them while I'm counting the number of moles. I will only consider the aqueous and the gases. When you are trying to find which is the direction with the less moles and which is the direction of more moles, like here, MgS plus O2 and give you 2MgO, and you are trying to find which direction has more or less moles, so you can decide what happens when you increase or decrease the pressure. Don't count this magnesium because it is solid, and solid is not counted. Only count the gases. This is 1 mole here and 1 mole here. So any change, sorry, this is also solid. So this is also solid. So there is only 1 mole on the left side. There is only 1 mole on the left side, and these two will not be counted, and there is 0 moles on the right side. If the reaction has a delta H, which is positive, or if the energy is placed in the reactants, then this is considered as an endothermic reaction. If the delta H is negative, or the energy is placed in the products, this is considered as an exothermic reaction. If you add any reagent in the form of ionic compound like FeSCN, then it's going to break down into the ions that's forming it. So if you are asked what is its effect, then it will increase the concentration of ions of Fe plus and SCN minus. In the reaction of nitrogen, which reacts with hydrogen to form ammonia, it's known as the Haber process. It's better to have a high pressure, because if you increase the pressure, the system will try to decrease the pressure. So it will try to move to the direction of less moles, which is the forward direction. This has 2 moles and this one has 3 and 1, so 4 moles. So it will move to the forward, increasing ammonia production or increasing ammonia yield. Although it is better if we want to increase the yield to decrease the temperature, because decreasing the temperature will increasing the temperature, so it will move to the direction which is exo, which is the forward direction. But decreasing the temperature decreases the rate of the reaction, which is not favored. So it's better to have a high temperature for this reaction, which will increase the rate of the reaction, because the rate of the reaction is more important than the yield. That's why the conditions of this reaction is to have 450 degrees Celsius and 200 atmospheric pressure, and then have finally divided iron as a catalyst to make this reaction faster.